Please give a warm welcome to Dr. Timothy Chung.
Good afternoon, everyone. My name is Timothy Chung. I'm a former DARPA program manager in the Tactical Technology Office. And on behalf of the Breakthrough in Field Robotics panel, I'm really grateful to be here and excited for the conversation that we're about to have. I think this panel in particular is really going to explore the possibilities that will what we're interested in is unlocking the breakthroughs in field robotics. One of the goals of this panel is to shed some light on the future challenges and explore ways that DARPA should potentially accelerate this development beyond what's been already accomplished. So along the way, I think we're going to seek to uncover some of the factors that have led to the successes, but also the failures of field robotics. The panel members here will also take a few minutes to describe a little bit about their background, which is quite storied. Lots of scar tissue and seasoned stories associated with their exploits in field robotics. And I think that will provide a glimpse as to the challenges that we're going to face, but we really also want to hear from the audience. What are the questions that you have about the nature of robotics and the nature of getting robots into the wild? The second half of the panel will also give that opportunity to go and delve further into those questions with additional comments. So I'm going to take a moment here to introduce our 4 panel members, starting first with Dr. Robin Murphy. She's a Raytheon professor of computer science and engineering here at Texas A&M, a TED speaker, and an IEEE ACM and AAAS fellow. And her fun fact, I'll say, is that she's a seasoned veteran of now 31 rescue disaster response scenarios where field robotics have played a very impactful role. Okay. Our next panelist is Dr. Stuart Young, who spoke earlier and then joins us from the DARPA Tactical Technology Office as well. And fun fact for Stuart is he's rarely happy when robots are going anything slower than, let's say, 60 miles an hour, 70 miles an hour. Okay, good. And our third panelist is Dr. Saripalli, J. Mike Walker, professor in mechanical engineering and director for Center for Autonomous Vehicles and Sensor Systems here at Texas A&M as well. Fun fact here is he started off with small robots, but now has progressed and outgrown and now working on 18-wheelers as from a robotics perspective. So a wide range of sizes. And our final panelist is Dr. Wennie Tabib. She's a systems scientist with the Robotics Institute at Carnegie Mellon. She specializes in perception, planning, and learning algorithms. And the fun fact for Wennie is she's also an avid caver. She's one of the only cavers I know who likes to bring her robots with her into the cave systems when she's going and exploring. So with that, let's get the conversation started. Thank you. I think one of the things that I'd love to start with in this conversation is understanding what it means when we talk about robots in the field. I know there's a lot of hype and a lot of robots in media and science fiction and the like, and I think it would be really great in this role for DARPA as a truth teller to help calibrate what we mean when we think about field robotics. And so maybe I'll just go out and ask, how do we all think about field robotics? What makes robotics in the field different than robots not in the field? I'll start with you, Robin.
Well, for me, the robotics in the field, it's a more unstructured environment where you can't engineer the environment to make it work around the robots. It's the other way around. The robots got to work around the environment more, which can be people, it can be the deconstructed rubble of a building collapse. It can be the traversing Mars. Those are the things to me that make field robotics.
Sure. So some of the uncertainty of those environments or the irregularity or the uncontrolled nature of those environments?
All of the above.
Yeah, all the above. Yeah, so Stuart, you operate, as we heard earlier, a lot of robots in these challenging environments. What's your thoughts on what defines field robotics?
Yeah, I mean, it's the same thing. I think, for me, it's dealing with the open world problem. And for me, it's really about dealing with the randomness, the stochasticity of what's happening in the environment. I'm always intrigued by when the robots do something really real. Is it repeatable? And when it's not, it's like, yep, we still have a lot of work to do. So it's dealing with that randomness, and I think the unknowns that we can't pre-predict when we get out of our comfort zone of our labs or whatever, where we're trying to deal with. We have very structured environments. It's the unstructured nature of the real world that just makes it fun and the huge challenge for us.
Anything else you'd add to that, Sri?
I think I agree with everything that Robin and Stuart has said, but I just think of it as robots that you want predictable interactions in unpredictable environments, right? Consists of 3 parts: hardware, software, and environment. Most of the times we think about the hardware and the software, but in a field robotics sense, you should be putting in enough thought about the environment and the unpredictability of that environment.
Yeah. Wennie, can you give an example of when maybe we've thought about the hardware and the software part ad nauseum, but not thought about the environment? Any experiences from that perspective?
Yeah. So when we took our cave robots out for the first time to Laurel Caverns, we were using a vision-based navigation system. But Laurel Caverns is a commercial cave. They've been digging out parts of it, and there was significantly more dust than I had anticipated. So the robot just couldn't take off properly because all that dust kept getting kicked up and caused issues with the navigation system because they couldn't track any features and it just keeled over. So knowing those edge conditions ahead of time is really hard and unpredictable. But it's critical to get robots to work well in those edge conditions so that they can be robust and safe around people.
Yeah, so what I heard was field robotics, you have unstructured environments, you have uncertainty, you have dynamics. These are some of the attributes. Robin, you just came back from Hurricane Ian and saw the aftermath. And can you tell us a little bit about what that experience was like and why robotics either struggled or were enabled there?
Well, the robots didn't struggle. The drones were incredibly useful. And there have been time, early in the, in the early 2000s, sure.
Sure.
What we see there is that every time the use case is different and the environment's slightly different. And so to get back to Sri's comment about the hardware, the software, and the environment, I'd add, what's the behavior? What's the goal? That task to really complete the ecology. And so what's nice about the disaster is at this point, this is about the 20th where we've seen really the 5th one with a large number of drones, and now we're beginning to converge on what the missions are. And beginning to see patterns in the damage and the types of missions and how you'd react. And that impacts, what are you landing? Are you using a fixed wing? Are you using a quadcopter, a hybrid? How are you deploying? Do you want to, what are your time constraints?
So what I just heard you say, though, was less about the technology itself, perhaps, but more about the field operations. Can you speak a little bit, I think all of us can speak to this, of how much of it are the technologies solved, or is it just getting our grad students to be better field operations roboticists, or is there something more from a technology perspective where we still need to have investment and such like that? Stuart, what do you think? I mean, well, operations are key, of course.
Yeah, well, I think 2 things. One is, as Robin mentioned, I think people talk about autonomy and they just say, "Oh, I want autonomous robots." And it's like, well, what do you want them to do? Yeah. And a lot of times people will say, "Oh, well, we're going to collect a lot of data." I'm like, well, what problem are you trying to solve? Because that'll drive what data I need, right? And so I think it's communicating that what specific tasks that we're asking the robots to do for us, whether it's manipulation or if it's maneuver. And then similarly, one of the things that I've really enjoyed with Racer is the opportunity to get those grad students out of their comfort zone of the structured environments that they're used to doing for their dissertations, and getting them out, and they're like, they have these aha moments of like, well, that's not going to work. And it's kind of like what Wennie talked about with, everything's perfect except for the dust, and now I can't see anything, right? So it's like being ready for that unexpected. And then I think, dealing with the uncertainty, it's like, my plan is I'm going to detect all these objects and everything's going to be great. And it's like, well, but there's uncertainty about all those objects, and you're probably wrong some of the time. And if you're too conservative, you won't get anything done. And if you're not risky enough, then you might have catastrophic failures of your systems.
Yeah, Tree, any experiences where the lack of clarity in a mission or task or something led you astray from field experiments?
I think as we do a lot of field robotics, we kind of understand so I think it's kind of like an iterative process. So we start off with a task, and then we kind of refine the task as we are doing this, because we understand a little bit more about what works and how we need to define the mission so that we can get the robotic system to work, right? But on that note, maybe not, the question that you asked before, if we have solved the robotic technology and if grad students need to be better field robotics, I don't think we've solved robotics at all. And I think the reason we haven't solved it is because it's a system science, and we have, let's say, perception, planning, and control broadly. I think people are working at each one of them, but they're not working at the interfaces of them. And that's the hard part of solving it, right? And if we understand that, then we can define the problem better. And if we define the problem better, then I think we can find the solutions better.
Sure. So as we've seen both in the news and things of that nature, where there's billions of dollars going into robotics, historically, we've seen well over a decade has gone by since the grand challenges and the urban challenges have really jump-started an industry as well. And we've also seen recently a lot of exits from that technology space, with a number of companies also going away. So what is it about, what can we take away from all of this money and then some of these companies also shutting down? What would you think, are there any takeaways other than the fact that robots in the real world are hard? Is there anything else that you might take away from that story? Rob, what do you think?
Well, I mean, go back to Sri again, and thinking is that we're getting a lot of robots that are robots, and now let's figure out what we're going to use them for.
Right.
I've got a robot, the aerial vehicle that can do delivery of what? For what? How's that? Where's the people? Where's the system? Where's the sustainability? What's the reliability? What are the regulations? What are that? It's like, oh no, but it's cool. Look what a great battery I have. Or look what a great rotor I have. Or I've got a new fantastic joint. So I don't know where you get robots that are, well, you build them, but I get vendors that say, here's your ground robot, and where do I put my other sensors? Oh, you don't, because we figured it out. So that's what I see.
Yeah, yeah, definitely. Stuart, what do you think? I mean, you're at DARPA right now. You get a lot of folks pitching ideas, a lot of things that you've seen in your own career and experience that hasn't worked out. Where is this trade-off between success and failure, despite billions of dollars being invested?
Yeah, well, I mean, the glib answer is it's a hard problem. And people who tell me when I'm working on this problem and they say, well, it's the self-driving community will solve that problem, I'm like, well, how many of you drove in your self-driving car here to this meeting? And they all say none. And I say, well, this is a reason for that. And for the problem that I'm trying to solve, and I think DARPA did an amazing job with the Grand Challenge, and we created this industry of self-driving. Part of what Racer is about is like, I want to try to bring them back to the root of the problem that the DoD has, which is, so it spawned an industry, but yet we still have this problem of dealing with it. In my area of passion is the field robotics, the unstructured environment. And I think part of it is because they took a brute force approach, depending on a lot of a priori information. It's the natural thing to do. I'm going to perfectly map these environments, and I'm going to have all this information ahead of time. Some of my friends would tell me, well, I don't have to follow the lane markers because I know where all the buildings are, so I know perfectly where I am. I'm like, oh my gosh, this is crazy talk for me. And so I think part of it is we have to solve the problem differently than the way that they're trying to solve it. I understand the way they went after it because they felt that that was the way for the low-hanging fruit, but I feel like we have to be better systematically and from fundamental root solving the problem in a different way. So for my world, we can't solve the problem in the same way because we'll never have enough data. We can't simulate our operational environment. Like I can simulate the static part of it, but I can't. It's very hard to to simulate or practice in, like, for example, Ukraine, as Melissa Flagg talked earlier, like that's a totally, like, how do I get the data for that and practice my systems there? Like, that's a near impossibility. So we're going to have to come up with different approaches to solve it.
Yeah, definitely. And I think kind of going back to Shree's point and the comments that we were all head nodding when we said it's a systems problem, and there's interfaces at the seams of these different subsystems. But if you had to pick, right, if you had to highlight whether it's the hardware side or the software side, I'm curious to hear where you see some of the biggest opportunities. Wennie, what do you think?
Well, I'd say it's a little bit of both. I'm really excited about a future where we have tiny drones. I can have 20 in my pocket and I can just throw them and they map a cave for me. But at the same time, the hardware has to not only get better, but the algorithms have to get better so that they can operate in dust, or the sensing has to get better so it can overcome issues with dust. So I think it's a little bit of both. And I think the combination of the two is going to make for some very exciting, nimble, agile robotic systems.
So is there something unique about field robotics? So I feel like in some ways we would want all our robots to get better, both hardware and software. What is it that's particularly challenging about the field aspect of field robotics? And does that bias one way or another for hardware versus software? Sri, what do you think? As a person who builds robots too, right?
Yes.
What do you think?
So I think that's a very interesting question. So what does the field, what does the environment give to that, right? And so I was going to qualify Winnie's answer and say that it's the intersection of hardware and software is where we should aim the most, right? So there are lots of fields, computer science that looks at software and things like that, and there are hardware, mechanical engineers, electrical engineers that look at that. As field roboticists, it's that intersection, because that's where the environment comes in, and that's the point that we kind of miss when we build robots. We don't think about the environment. We build a robot and then we put it in the environment, right?
Yeah, I remember, still having to wrestle with USB connectors or like all the interfaces. And when you say interfaces, we're not only talking about connectors, we're talking about how data is reasoned about or implemented, actuated, things like that. But it's always those darn interfaces, I think. So, Stuart, I think from an interfaces perspective, however, who can, or which organization or which perspective can bring about a better way to think about interfaces?
Well, I've talked about this topic a lot, and I guess I tend to be more, it's on the software side a little bit, and which is hard for me to say as a mechanical engineer at heart. Right. But I think that just understanding the world and then the problem. So I think as Sri said, it's really going to come down to this interaction between the two, and I think that there is a unique opportunity for us to, and it was tried before with some of the formats in the past of defining these interfaces, and I think there's still a lot for us to learn about what these interfaces should actually be. There's a lot of talk about flexible interfaces and modular open systems architectures, and I think that's a little bit cart before the horse for our domain still. But I think it's going to have to be a combination of industry and, for example, government working together. If you want to go down that route, industry has to have a vote because they have to be able to participate in the process. And just like all standards bodies, it's got to be a unified approach. But if I think we're still peeling the onion back as far as what that interface really needs to entail. And I think that's why some of the work that Robin's been doing for so many years, on that particular domain of rescue and things that we've learned in the past on UPI and other programs, there's just still a lot for us to uncover in that domain. And I think it's going to just come down to we're going to just have to continue to work together, industry as well as the government on that.
Sure. So kind of moving the story along, there are many places where we might think of robotics or many applications out there, but that have not historically leveraged field robotics to be able to accomplish the mission or tasks. Are there any in particular that stands out as fertile grounds that wasn't intended to be an agri-robotics pun. Is there any arena where you think field robotics stand to deliver outsized impact? Robin, any particular thoughts? Certainly rescue is top of mind typically. Are there other arenas that you can think of?
Well, disasters, fortunately, are rare. I mean, relatively speaking, the bigger wins is our critical infrastructure. And that, to me, is one of the biggest things. So as we were part of the team that was there for the Surfside collapse, and what was it, just 60 minutes on Sunday night talking about they're still trying to figure out what happened, but oh, look, there's these other condos that, whoops, perhaps may be equally vulnerable. And we have the bridges in the United States hitting their 75-year mark. A lot of those have very hollow pilings that have never been inspected, but specialized robotics could. So I think those are some problems that have just not been addressed. They're not particularly sexy, yet the cost of a failure is very high, and the cost of repair increases exponentially because it gets harder and harder to fix.
Sure, yeah, no, that makes a lot of sense, and I think what we're seeing in the maturation of a lot of the sensor technologies, perception algorithms, the autonomous capabilities of scanning or whatnot could really have a high impact there for sure. Yeah, Shri, what do you think? Do you think of any other places where the audience is really keen to hear, right? To know where we can go and.
I was going to say agriculture, but you took away agriculture.
You could do agriculture, go for it.
But I think I really think human-robot interaction, right? What we call as cobots is. So that could be field robots, because I think getting to true autonomy, however you define it, is very, very hard, right? And we really have no idea how to get to true autonomy, right? So you can get to 90%, 95%, or really when you define a task, you can, again, come back probably to the mission-specific task. There are some things that humans are just good at doing, and even if the robot is really good at doing it, we probably don't want it to do, right? So I think that interaction is, if we can define that better, and if we work on it, that's something that will, I think, push robotics forward.
Sure.
And right now we are still in nascent stages. There's a lot of research going on in that area, but we're still in nascent stages in that area.
So, but I'm thinking about that, and it's a tremendous point. So you phrased human-robot interaction as kind of we got to figure out how to build the robot correctly and share the autonomy or the task, the basic design. But it seems like we're forgetting this dichotomy between, is it the software, the hardware, what are the interfaces? It's like the way technology gets adopted is whether it's useful. It's not how, it's not how great the parts are. How many of us may know what the chipset is inside here, but majority of people don't and don't care. It works and not work. That app work, not work, right? Those things. And we're not there yet with robotics. And we don't have, and back to that whole systems that you've been pushing for, Stuart and Wennie, is that approach, training our students, training our designers and manufacturers. What is the problem we're trying to solve? Are we trying to build the coolest robot ever, which sometimes is
awesome,
pretty awesome, or are we trying to solve X? Are we trying to, and we know what people, we've got models of adoption, diffusion of innovation, usability. We've got the UTAUT model of how people in particular adopt technology. And it seems like we kind of ignore that as we build robots.
Yeah.
I was just going to say, like, one of the problems that I see is it's kind of related to what you're saying, Robin, but there's a lot of people that just talk about robots at a very high level and do some magic hand waving, and we have to figure out what that pixie dust really looks like. And so, it's like from the DoD perspective, I think they have this notion, somewhat of a panacea, that they want autonomy, but they don't really know what they want the robots to do. They just know they want them. And they have ideas of what they mean, but they don't know how to even instantiate the requirements, not to lowercase r, of what they would like the robot to do. And so I try to challenge them, no, tell me what you want, but you don't use, don't use autonomy, don't use machine learning AI. Like, that's how I'll solve your problem, but what do you really want? And so I think, logistics, to your previous question, is one of the areas, like especially in the ground domain for the DoD, is an opportunity. Even in the air domain, is an opportunity to really make an impact. And we know in the commercial space that a lot of companies have been exploring that. And so the idea is that we know that technically, we can make the problem simpler by adding some structure. We can exploit that structure. Anywhere we can do that, we have earlier opportunities for wins. And this full autonomy, like Sri said, is like a little bit further off. So trying to help them understand what they're actually asking for. Like, it's more than just a binary, like I have a robot. It's like, does it work or not? It's like, well, tell us what you want it to do and then let us try to see if we can make that real.
Yeah, I think that interaction is particularly key because humans and robots will be cooperating quite extensively, and we see that certainly in the DoD needing that kind of capability. So human-robot teaming, but actually, what is it about human field robot teaming that makes it, I'm going to keep pulling on this particular thing so we can elucidate what still needs to be done. So Wennie, what is it when you're thinking about your micro drones or nano drones that you want to deploy, what is it about the partnership that you will be entering into with these teams of robots that are particularly unique?
So one thing that's really annoying when surveying a cave, for example, is getting into those really tight passages where you have 16 inches of space to work with. But right now, if you look at local exploration approaches, they all maximize volume. Mm-hmm. So effectively what that means is your robot is going to go towards the most open area and leave you with all the terrible passages to map, on your belly. And it makes sense if the robots are operating alone, but if you're working as a team, that's not the behavior that you want. So we need some way of communicating goals between the human and the robot in maybe an implicit way, because the human might be preoccupied carrying something, and so we need to develop more techniques to leverage the intelligence of the human for faster task execution.
Yeah, no, that certainly makes sense. And so field robotics, again, coming back to field and what it means to be in the field, we said uncertainty, we said dynamics, we said unstructured. How much of it has that spatial element? I was thinking about it because you said the 16-inch holes that you'd have to otherwise send robots into. What is it about the spatial dimension? Is there any element that's unique about the spatial dimension or the timeliness, like the time sensitivities that factor into these environments when we think about field robotics? What do you think?
Well, I think field robotics means a lot of things, but certainly in disasters, and if you look at, let's say, interior of rubble, now you've got all sorts of size constraints. You already started out with time constraints. You've got about, 72 hours, 52, 72 hours to get a survivor out. But you're looking at, you started referring to things, 16 inches, right? A person might be able to get through that space. But we've never developed, as a field, anything equivalent to a Reynolds number for saying what's the size of my robot relative to the environment it's going through. The ethologists, they can track mouses and say, hey, here's the tortuosity, the turns. We can rate ant tunnels, but we don't do that for robotics or field environments. So we have no metrics. We build test beds with, okay, it's wood because it's cheap, and it's this big because the last one we saw was this big. And it's like, that's not a very principled way of testing. And I think that's one thing that's holding us back, is the field for the type of work I do and that Wennie does is very hard to characterize. And it's not one of those things where, we'll build a simulation. Okay, again, how big? How is that relative? Where's that Reynolds number?
Interesting. Yeah, so Wennie and Robin talking about tight spaces, Stuart and Sri thinking about being able to transit or work in larger spaces, larger spatial dimensions. It would be great if there was that dimensionless parameter that can kind of characterize all of those. I think maybe that's
one
to, the
one that comes to mind is SLAM. Is it's great until you go a long way and then your system breaks down because you don't have enough compute, or you have this long loop closure problem and all those different challenges in the open domain, which are different, but we still use the same tools and the same math for those problems. And it's one of the reasons why the bigger spaces becomes a problem over time. You know, things start, you know, the air and the drift and everything starts just working against you.
Yeah. No, I like this idea of a science of field robotics. I know there's the science of robotics that we're moving towards, but the science of field robotics that allows for a system engineering almost holistic approach where there are these types of metrics and things that could really help drive technology. So maybe that is a great question, focusing on, are there partnerships or approaches between government, you spoke to this earlier, Stuart, government, academia, industry, coming together to solve audacious challenges in field robotics? You know, the way the DARPA grant challenges and other challenges have really helped drive the technology. Are there any that come to mind that you think could be of high interest? So this is our opportunity to pitch the next DARPA challenge potentially, or think about what the characteristics of that might be. I tend to think of wider area or time criticality, of a lot of uncertainty or diversity, low probabilities of detection or high probabilities of false alarm. Those are attributes that I tend to think about. What do you think we could have partnerships go explore?
Well, I think that one of the things that interests me is looking at the seams between some of the classic problems. And so, for example, locomotion mechanisms that can span multiple biomes, for example, that's not optimal for one, but is maybe suboptimal, but can do both, I think is one opportunity for us to explore that space, to get clever new ideas. And so I think there's a couple facets to the question was government, industry, and academia. I think, the government on one side, we can bring the problems, part of the problem space or a proxy for the problem space. I think that we critically need academia to work with us because of the innovation that comes from that ideas, but I don't want to leave out the industry part because at some point we have to build these things, and academics aren't necessarily doing that part as well. So I think there's this combination that kind of gets to this, it's like this multi-objective optimization that we all love to live in every day. I think that's part of it. So, whether it's new locomotion mechanisms that we haven't, I think there's a lot of space to explore in systems that were never built for humans to be on, to be a part of, not just obviously the small ones is the case, but even on bigger systems. What are we, I feel like there's some dimensions that we're not uncovering yet, and so that would be something that we could really go after. And I think all of those that you listed, participants, government, industry, and academia could, really play a role in that.
Yeah, so as we have a number of academicians on stage here, what are some of the places where academia, Stuart called some out, but what are the places where academia really can help accelerate or drive some of these technologies? We'll start there and then progress through. What do you think, Sri?
I think one of the main things, and I want to be careful here, I don't want to call it architectures or things like that. So if you take like ROS, Robotic Operating System, that was a bottom-up approach that was started literally by two PhD students and now is used by pretty much everybody in the world, right? Mm-hmm. And that was because academia realized that there isn't a good way to actually give tools to everybody to solve the kind of the basic problems that are there in robotics, right? But I think there should be a push and pull, right? So if you just leave academics to come up with solutions, every academician will have their own favorite solution. And so ROS became good because it got funding from industry and then also from Department of Defense that put in a lot of money into ROS, right? So both the industry and DoD saw the advantage, and DARPA saw the advantage of using ROS. So I think those are the kind of things. You want academia to kind of foster this open, again, I don't want to say architectures and I don't want to say APIs because both of them have bad connotations, but I think those are the things where academia could excel quite a bit. And of course, solving the really theoretical problems, right? So the way we think about probability right now in robotics is not, we don't think about context, we don't think about what comes after next. So there are still fundamental problems in robotics that need to be solved. So there's one about fundamental problems and the one about, say, open source technologies, let me put it that way, that I think academia could do.
Yeah. Wennie, have you seen some of those things kind of manifest as well?
Yes, and I think another, to add to what you said, a big challenge is just, as a roboticist, you have to be, especially a field roboticist, you sort of have to be a master of all trades. Mm-hmm. And that's very difficult for the average person. So I think one of the key investments that need to be made is just how do we get the technologies into the hands of people who are not as deeply familiar with the technology as we are. For example, like sub-T, how many engineers had to be on site in order to monitor the system, make sure things were operational? How do we get to a place where we can hand a robot to a soldier and have them use it and not break it on the first try?
Right, for sure. I think by the way, this is a great time to encourage additional questions coming in. We're seeing them all come in from the audience, but I'd like to remind the audience to go ahead and submit additional questions. One of which, for example, what are the gaps in the technologies when we are thinking about longer term autonomous system capabilities? These are things where you don't have the ability to engage or you don't want to engage over long periods of time. What are some of the technologies that we need to accelerate to see that come to fruition?
Oh, well, reliability, right, you have to have that, but both hardware and software. But also there's this gap that we're seeing of not being able to predict success. You've got particularly in a long duration of it, it's not just one region, one work envelope, but like you were talking about, Winnie, with your cave where you've got the dust. Well, if you've gone further, then that may have cleared out. And then the envelope changed as well as the surface properties and things. So being able to handle those, that resilience and adaptability, are things we haven't done well, and we haven't done well at predicting and knowing what our pinch points are.
So how would we exercise, how would we exercise that in order to accelerate the technology? In other words, how do we predict the unpredictable or get our robots to predict the unpredictable? Is that an algorithm?
But is that unpredictable? Is it just something that we haven't considered the data on, either the hardware constraints and run the probabilities or the consequences of failure? Mm-hmm. Likewise, we haven't characterized the environments, that sort of thing. So I think that's
part of it. Yeah. What do you think, Stuart?
I think the thing that came to mind when I saw that question was, power, and Carrie's talk earlier today about, we're so fixated on we don't last long, and a lot of times it's because of power, especially like batteries, especially on the small robot side of things. It has been the bane of our existence. It's getting better, but we're not really looking at how could we harvest the energy along the way for those longer term missions, like what Carrie was talking about. How can we exploit that and get behaviors that's part of their objective, is like they have to self-feed themselves along the way, in addition to the system being resilient to unknowns or even self-healing in some aspect. So I think that's a huge opportunity, and also to use, and this is where academics could really continue to play a role in, obviously industry on the power side, but also just coming up with new approaches, like for more efficient muscles and more efficient actuators and stuff that has been a problem for some locomotion mechanisms that we'd like. We're just the efficiencies could be better and use the power more efficiently, but how we go about solving the problem, I think is power is always kind of one of those dimensions of field robotics that always bites us, because in the lab it's like, well, I'll just put a new battery in real quick, and it's like in the field robotics, like that's part of the problem.
Sure. Okay. So I heard resilience. I heard maybe self-sustainment or self-maintenance even, right, to some degree. Sri, what do you think? I mean, where else do we need to really accelerate?
So, it's an interesting question, right? I think one of the things that, yes, so I first agree with both those things. But I think an interesting way to look at it is if I was taken and put in a place where I had no idea where I was, and I was asked to move, I think I first start thinking about, yes, so do I have food, water, things like that, but then I start thinking about risk. Can I stay here, right? So we have not incorporated risk into what we do in a principled way, right? Sometimes you want to be very risky, and it's okay to lose your robot. Sometimes you want to be very safe, right? And how do we do this trade-off? Humans are very good at doing this trade-off, and it comes from experience, training, things like that, right? And we don't have that. And I think that's from a more like technical perspective, it's something that we need to think about.
Yeah. Do you think that's a algorithmic question or a perception question? I can see risk manifesting in a lot of different ways. What do you think?
Being a field roboticist, I put it in the middle. So perception, planning, control, you want risk in pretty much, and it's kind of like a loop. So it's not just at the perception level. It's how does perception feed into planning? How does planning feed into control? And how this loop kind of does. And of course, humans, right? So what if somebody came in and said, hey, you need to be very risky now, right? So that mission parameters, right? So lots of things. But yes, I would say that it's the interface between perception, planning, and control.
So I could just add, so you mentioned that humans are really good at risk management, and I would argue that older you get, the better you get at it. So like there's some notion of experiential, and in a lot of sense, we're still very infantile in our in this field. It's a new field.
Yeah.
Our young kids don't necessarily manage risk the same way we do. So I think there's this element of experience that we're not capturing as well as we could, like, whether it's long-term memory or how do we take advantage of that, I think is a big area for us to continue to work on, and that equates to the risk management.
Yeah, interesting. Wennie, what are your thoughts? We've got resiliency, we've got self-sustainment, we got risk awareness.
Maybe redundancy.
Okay.
Instead of one long-running system, you can have many systems that swap in and out. Maybe a different way to look at the problem.
Yeah, so strength in numbers and redundancy, being able to do that. Yeah, interesting. Cool. Just coming back to battery, because one of the questions just came up is, what are your thoughts on the promises of robotics and the limitations that battery technology presents? So that could be its own 45-minute panel just talking about battery power, but just thinking about endurance, what are some general thoughts from your experiences? Yeah, I mean, Robin, how frequently are you seeing folks have to swap out their batteries, and that being the limiter for rescue robotics capabilities?
For the aerial vehicles, it's not. You're swapping out the batteries. The bigger thing that we see impacts adoption is that the smaller drones can't carry as big a payload, but you can recharge the batteries. The batteries are cheap, and you can recharge them in your car.
Yeah.
So you can go out in an SUV or a fire truck, and you can go all day. You get one of the larger, more specialized batteries, you better have a generator that you're also taking. Oh, and now you got to take the gas, and now you get to, and so you've just logistically shot yourself in the foot. And even better, those have maybe what, 20, 50 hours run cycle, and then you're buying a new expensive, highly specialized battery. Yay, team. So that's some of the things that we see with the batteries. Now with the ground robots, we're running off of tethers because we're having to go down, around, up and down. We need, in the highly confined space, we don't have wireless. So we've got power, we've got wireless. We're good for those. Just swap out a car battery with the next one, we're good.
Sure. Wennie, when you're going in these caves, do you take a bunch of spare batteries with you? Is that how that, I mean, I know for your lights, you take sets of 3, right?
Right,
but
yeah.
For your robots, how do you deal with battery management?
Oh yeah, we take a ton of batteries, and usually we recharge them off the car.
Yeah.
So just pop the hood, attach it to the car battery, and recharge that way.
Right. I suspect this isn't all that different from our warfighters who have to haul in batteries themselves or other power sources themselves. So again, like you're saying, logistics, it's a logistics problem that comes.
Right, the PackBot, all of a sudden one day we're using the radio batteries. Are they optimal for ground robots? No. Are they easy? Does everyone have one? Bunches of them you can find? Yes, they said make it work with these type of batteries because it impacted usability, right? That larger work system, not just coolness factor.
Yeah, no, for sure.
I look at it more as like just this ensemble, like we talked about powering, recharging them in the car. It's like, to me, it's like that recharging of the car is part of the whole system, right? So it's like this hybridization approach, and just, in field robotics, it's just another constraint that we have to deal with. So it's power management or energy management, and we also have to deal with communications management. You talked about tethering. It's like, well, there's a reason you tethered because of, either power or communications or getting signal out right. And so we're always having to manage it and look at the trade-offs of the maneuverability and the possibility of getting, and when you start getting it bigger. So I start looking at this where like opportunities for teams of robots in the field problems. Like some robots could be tailored or optimized for some tasks, and then it's the collective that allows them to address the problem.
Sure. Yeah, no, so I'm really excited. What I think I've heard is that we need resilient, self-sustaining, risk-aware, redundant systems, and then we'll be able to have finally solved the field robotics problem. I think that's what I heard, right? So with that, I think we're near the end of our session, so I think I want to go ahead and thank our panel members here for this conversation. I encourage you to reach out to them during the breaks or afterwards to be able to further this conversation and pick their brains about the future of field robotics. Thank you, panelists.